Hello, this is Dave Spicer, and I'm here to talk with you about a new technology called IdentityJS. This is a portable platform as a service technology supporting public, private, and hybrid configurations to reduce cloud development and maintenance costs by a factor of 10, and will also boost server performance by a factor of 2. If you want to learn more about IdentityJS, all of it is included at a website called IdentityJS.com, which happens to be built out of its own technology. So by visiting that site, not only you learn about it, you'll actually be using it. Questions, of course, can come to me at dave@identityjs.com. So let's get started. Just a quick outline. Start with first principles analysis and kind of the reason for doing IdentityJS in the first place. Talk about today's cloud architectures, private and public, the way today's systems operate, then the way IdentityJS rethinks this architecture and uses infinite elastic scalability to achieve a lot of its goals. Then talk about single source for all servers. This is why it's called identity. There's one set of source for all servers you're running on, clustered or unclustered. Then there's also single source for all clients, meaning browsers and smartphones, both browsers on the smartphone and native apps on the smartphone, all from one single source of code, which is where a lot of the productivity gains come from. Then lastly, talk a bit about software by reference and the way we use shared JavaScript object libraries. So let's start with first principles. Technology exists to increase human productivity, and that's been the role of technology for a long time. Software technology specifically has been doing a good job, if you think about it, from spreadsheets to today's artificial intelligence. You can imagine the kind of productivity boost spreadsheets gave to the accounting folks back when that was the killer app of the PC. And today with artificial intelligence, I think we'll see the same kind of productivity boost. But now, the applications that increase productivity are themselves very labor intensive to build and maintain, which means they're ripe for improved productivity. IdentityJS is targeted at this productivity for today's cloud-based systems, including significant performance improvements in terms of the runtime efficiencies. So let's look at the way systems are configured today. On the right-hand side, we have servers, and they might be private behind a corporate firewall, or they could be public, meaning they're behind a commercial cloud vendor and shared amongst lots of customers. These are the typical commercial cloud vendors you'll see. Over on the left-hand side, we have devices accessing these servers, and they're either smartphones like Android or iPhone, or they're browsers which can run desktop or mobile. So it's a mix of browsers, desktop and mobile, and native applications running on smartphone devices. And they communicate over the internet. So if you think about systems these days, they all fall into this category. More and more companies are putting their private servers into commercial cloud environments just so they can offload the special needs of managing these environments, which become especially sophisticated when you consider fault-tolerant, no single point of failure kinds of architectures and what it takes to maintain those infrastructures. So basically what we have is a ping-pong match going on between the devices on the left and the servers on the right. And if you could peek inside of this network, what you'd see is a lot of traffic, typically a small amount going to the right and a lot of traffic going to the left back to the devices. Simple example, you have a URL you type into the browser, it gets sent to the server processes that and sends you back a result with a web page and perhaps some data filled in. It depends on what the application is doing. You then click on something or enter something on the browser from that point. That information gets sent back to the server. Server processes that and gets you the next piece of information. Could be a new web page, could be something filled into the web page. And it goes this way on while you're using your application to the end. So this is a ping pong game here from client to server and back again. So if we take a look at a system today, let's use something that we all know and love, and that would be Amazon.com. So here's Amazon. And let's get a fresh copy of it just to make sure we're current. And you can see it's mine, so obviously they're using cookies to remember it's me that last accessed it from this machine. Now, all we did was we'd entered a URL to go to Amazon.com, and now what we want to do is take a look at what got sent back as a result of that request to get this display. So what we can do now is go here and view developer source. And here we're going to get details of everything that got sent back to us with that simple request. And it looks like there's a lot here. And if it looks like a lot, that's because it is. In fact, what we're going to do here is get a count of this. But basically, what's happening here is Amazon, because of my simple request, has sent me back everything that the browser needs to display that page. So it's not just sending back the data for that page, it's telling the browser how to render it. So the detailed user interface work was done by the server and is being sent back to my client. So let's find out how much we got here. So I'm going to copy that information. I'm going to put it into a little text editor I have called Text Wrangler. And we'll see what we get here. Okay, so if we look at the bottom here, what we're seeing is that that simple request resulted in 546 kilobytes of information being sent back to my browser, which struck me as being odd because what it's really telling us here is that we're doing all the work on the server and not using the client device, be it the smartphone or browser, to do much of anything. So let's go back to our picture here. So what happened is we sent a request, the machine processed that request, and sent back half a megabyte of information to my device. Now, if that sounds extreme, it really is. And there's really three things wrong here. First of all the knowledge to do the rendering of the user interface is on the server. And this is true whether you're using PHP or Java with Spring or ASP or the variety of different technologies, all of which are server-side and are doing the same thing, rendering the user interface here and pushing it down the pipe to the device. So that's one thing. We're using too many resources here. Secondly, what's happening is we're not using the resources here. We have these resources here that are free. Okay, so as far as my application on the server is concerned, anybody who's using that application, their device to me is a free device. I could use it to do some of the work. And then of course what we're doing is we're pushing down a half megabyte of information from the server to the client, which in the case of a desktop browser might not be so bad, but if you're on a mobile device, you're pushing lots of information to that device and potentially eating up the poor customer's data plan and process. So what I want to do is look at a different way to do things. And what that is rebalancing the way this works. So let's take a look at one more example and do something else that other people would do, and that might be Facebook. Let's try another one. Maybe Facebook won't be quite so bad. I'm curious myself. Okay, so this is my Facebook page, and again, I'm going to get the source, and it's thinking about it. There it is. I'm going to copy, and we'll paste it back into my little text wrangler editor here. And let's see what we get. Wow. Okay, so it's even worse. This is 812 kilobytes. So, wow, I thought it would actually be less. I thought Amazon was high. Okay, so this is typical though, and I think you'll see some examples where it might be 100K in some of these applications. But nonetheless, it's sending lots of information back to your device. So in summary, there's 3 things going on here. With regard to the server, we're using too much server. On the client side, we're not using enough. And the result is we're basically killing the network with way too much traffic, a lot more than we really need, because over here, we could be doing a lot more work than we're doing here. In the case of Amazon, what happened if you happen to use their system during their Amazon Prime Day, they were trying to support millions of users, and at 12 o'clock West Coast time, they turned on their Prime Day support, and immediately about 6 million people tried to request it. And of course, 6 million people requesting a half megabyte of data getting sent to them from the servers basically caused it to fall over. So if that ought to be a clear indication that there's got to be a better way, and in fact or at least one of the ways that the thought came to me, there's got to be a better way to do this, and that's where IdentityJS came up from. So let's take a look and see how IdentityJS does in these examples. And to do that, I'm going to bring up the browser, and this is IdentityJS, the production version. And while I'm here, I'll show you this same site running on smartphones. So right here, I've got my Android machine, and this is actually a live machine connected to my laptop here, so I can share the display, but this is not a simulation. I have to emphasize that. This is a live machine, and we're going to bring up the Chrome browser and show you what IdentityJS looks like. So this is the same site, IdentityJS with single set of source code, and it's being used for all browsers, desktop, all the versions of the desktop browser. And here it is on the Android browser. Now let's do the same thing for iPhone. We'll bring up the iPhone over on the left, and we'll bring up the browser here. So here you have it in the Chrome browser on the iPhone on the left. So again, I'm going to just scroll through on both sides. You can see it's actually a live system. So now what I want to do now is show you how it looks as a smartphone app, a native app. So I'm going to go over on the left-hand side. I'm going to bring up my application running IdentityJS. Now, how do you know it's running in the native client? Well, you can see all the headers are gone, and it's taking up full screen. Now let's do the same thing on Android. We'll go over to the machine on the right here, and do the same thing. And there it is. So we're now running the very same software on all browsers, regardless of type, on the desktop or laptop, and as browsers in both smartphones, and as native apps in both Android and iPhone. So we're going to put those away for a moment, but you get the idea. It's one set of source, which is why it's called identity, and this is emphasized in the clients, but also one set of source for all the servers, regardless of the server mix you have. So here's IdentityJS, and let's refresh it. And now let's take a look at the metrics here of how much it got sent. All right, so let's do the same test here. We'll copy it, and we'll paste it into text wrangler. And lo and behold, down here at the bottom, instead of hundreds of kilobytes, it was 800 bytes. So basically, it's relative to Amazon. This is 500 times less traffic being sent to the device. Now, how is this possible? Well, basically what I've done here is put all the UI work on the device itself in JavaScript. So what you see here are the JavaScript libraries that are cached so that I only have to read them once. And obviously these will stay cached for a long time. And then all I'm doing here is that you'll see that there's no body involved here. So those of you who are familiar with HTML, this is where the body of the HTML goes to render the display. And of course there's nothing here. And so what's really happened is at the time I brought this up, I've called an identity boot JavaScript function, which is what kicks off all the rendering of the display that you see. So if we go back to our display, what you see here is the complete system, and it only involves sending 800 bytes down to it, less than 1K. Now, of course, other applications could vary if you have more libraries involved, but you're not going to see anything like 100 kilobytes, okay, or rather 1,000 kilobytes. So what we have now is a single system. That's some of the things I should give a little tour here. So IdentityJS, here's the main application. With any IdentityJS application, you can get a link to the identity node that's actually being the server. So if I click on this link here, it's going to take me to another application which actually connects me to the node, identity node that I'm using to process my requests. And of course, if I have a login ID, I can use it. But I can also go over here and look at all the release information for all my libraries. I can also look at all the web services that are defined, get their descriptions. If I close this, I'll go back to my application. Now, the other thing to point out here is what's something convenient about IdentityJS is that it's actually a container. And I use this word, it's different than, let's say, a Docker container. It's a container that supports multiple applications. So as I showed you, any IdentityJS application, when I click up here, I can get a path to the console. Well, just for fun, since the console is just another application, I included it in this application. So you can have as many applications as you want stacked up here. And every time you click on one, you get the appropriate menus for that application. So if I click on console, I get their menus. And if I go back to IdentityJS, there's its menus. So this would be convenient for companies. Some companies will have many, let's say several applications, thinking about smartphone now, where they'll have one for customers and then one for maybe their internal users. And with this technology, you can actually share that application, put all your company applications into one container. On the server, it runs inside a Docker container. And on the client, it runs in its own container so that you can have, again, stack these up and you can have as many applications as you want. This will scroll if you have more than two. And here's all the menu items for each application, which will scroll if you have more than you need that will fit in here. So I think you get the idea. Okay, now let's look at what all this means in terms of development and maintenance. And for example, let's take the cost of making a client change in the software. So let's look at the current situation without IdentityJS. And even making a simple change requires all these steps. Okay, so this is assuming you've got, you're supporting browsers and smartphones, apps for both iOS and Android. So with iOS, you have to use Xcode to make the change to the Objective-C source. You have to build the code. You have to test with an iOS simulator to work through those bugs. Then you have to test with a real phone. And sometimes you even have to test with a dev phone, right, a development mode phone. So there's lots of testing going on and repeating those tests over and over again. Similar with Android, although it's different IDE, right? You've got to use the Android IDE and make the changes to the source code. They're typically using Eclipse as their IDE. You then have to build the code, test with Android Simulator, possibly test with the phone in dev mode. Then lastly, you always have to test with a real phone because your users aren't going to have development phones. And then next step, of course, is the browser. You need to make sure it works in all the browsers, making a different source code change. Test with iPhone and Android browsers as well. So you have desktop browsers and mobile browsers to test with. Then you have to submit it to the App Store and wait for the App Store approval process, which can take longer than the Google Play approval process. Or actually, Google doesn't really have an approval process, but it takes, in my experience, several hours. And with App Store, it takes several days. Then all that is done, you have to wait for Google Play to do the distribution. And at the end, you can finally distribute the browser version by pushing your code to your server. So lots of steps, lots of testing, even for the simplest of changes. So now let's look at what you need to do if this is an IdentityJS world, because it's a single source, all the code is identical. You edit your source with your favorite editor. You're not constrained to use Xcode or Eclipse. You can use whatever editor you like. I mean, some people like a little editor called Brackets. There's all kinds of editors out there that people use. You test with a browser, and I do all my testing usually with Chrome, and I do some. After that, I'll do some cursory tests to run it through things like Windows Internet Explorer, and even though that one's going away, we support that one. But typically, you just have to test on one of the browsers, whichever you're using for development. Test with real phones. I'd say you want to test with both iPhone and Android to be safe. But again, there's no simulators involved. There's no dev phones involved. You're testing with real phones. So your developers can be testing while they're at lunch on their real phones, right? And at the end, you push updated library to your code server, and everything that's referencing that code server will immediately update. So you've got continuous deployment here, so and across all your platforms. Huge cost savings. So we've been talking mostly about the client side. I want to switch over to Identity Cloud and spend a little time on what's happening in the cloud server area. So the architecture here was inspired by something called graph theory, for those of you who still remember your discrete mathematics, and where a graph is a set of nodes connected by edges, and in this case the edges are web services. But that model is a very good one to have in mind. If you're familiar with graph theory and the concept of nodes and edges, it's very convenient when you're talking about these kinds of systems. It's open and extensible, just like on the client side. Everything's JavaScript and object-oriented, so you can extend everything we've done. It's fully object-oriented JavaScript, so it means we have taken standard JavaScript and extended it with a helper function, a very simple design pattern, and the same technology works for client and server. So the same architectural concept of object-oriented JavaScript as we described it here is the same for both clients and servers. It comes with JavaScript web service infrastructure, using JSON as our marshalling technology. So we use JavaScript forward and backward to the server and back again. And two kinds of semantics. At least once, so we do guaranteed delivery. At least once is the default, and only once for those transactions that need more than at least once kind of capability. So examples would be a banking example. At least one would be checking your account balance, where it's okay if that transaction were to run a second time. And if you were to do an account transfer of funds, then obviously that one is only once and only once transaction semantics, since you don't want to run a second example if in fact a response got dropped. So we support both those built into the infrastructure. And then there's the issue of software by reference. So like synchronizing data, think of your calendar and your email as examples of synchronized data, where if something changes on your server, let's say it's a calendar item gets added to your server, regardless of what device you're using, you see that change. Well, we're doing the same thing for your code across all platforms, making it accessible by reference from a centrally managed URL. And at the end here, just talk a bit about recursion. IdentityJS, as I mentioned before, is built from itself. So all the things we're talking about, recursion of software by reference, things like that, all the benefits of that apply to ourselves as well. So when we make a change to one of our libraries, everybody referencing that library gets that update instantaneously. So let's look at the architecture of Identity Cloud, and in this case, specifically an individual identity node. All of this technology is based on something called Node.js, and those of you familiar with the latest server technology will have an appreciation for what Node.js is. It's basically a JavaScript environment built on Google's V8 JavaScript engine. And what we've done here is build the entire system on the server side out of JavaScript, writing on Node.js. But of course, we don't want developers to have to understand Node.js at all. All they're doing is writing web services and event handlers to process transactions without having to know anything about Node.js. All of that is taken care of for you. So over on the left, we have a network interface with an IP address. We have workers listening to that address. And we have one master process for each node that does not handle transactions. It's strictly managing workers. So it's creating workers, managing their health, restarting them if necessary, stopping them when necessary, that sort of thing. And all of these workers are stateless, which is how you have to do clustering if you want to truly make the system fly. So, but then it begs the question, well, where is state saved? And in the case of IdentityJS itself, state is saved in a Redis database. And most of you, I suppose, are interested or familiar with Redis. It's an IP addressable, real-time, clusterable database, very fast for relatively short non-SQL-like access. Very high performance and ideally suited for this particular application. Now we make Redis available, the same instance of Redis available to applications who want to run in this environment. So they don't need their own instance of Redis. They would just run in their own namespace. And of course they would add Oracle or other application databases out here for whatever their application needs. What we want to do is make sure we don't require anything more than what's absolutely necessary. So Redis database is absolutely necessary because we need it for our internal state, which allows these workers to be stateless. And the other thing you'll see that's missing here that you might be looking for is where is my web server and app server? I don't see Tomcat or Apache or Glassfish or WebSphere. Where are those things? Something has to handle the interface to the IP address here and invoke web services or access the actual files when you're operating as a web server. Actually, what's happened here is we were able to make that small enough that the app server and web server combined are actually distributed to each worker. So every worker has its own app server and web server listening to the same port here. Okay, so that means transactions, when they come in, they're handled by the next available worker. They're processed. Any intermediate state information is stored in the database. So the next piece of the transaction or next thing that happens, it doesn't matter which worker you're running on. Any worker can process any transaction and have access to all the same state information in the Redis database. And These workers, as you can see there, you can specify any number of workers per processor core. So there's a parameter when you set up to specify how many workers per core, and that's how many workers you'll get here. So again, this is all sitting on Node.js, and it's all in JavaScript, including our code. So that gets you clustering internally. So every identity node is internally clustered. But that begs the question, what happens when that machine runs out of capacity? So clearly there's a finite, regardless of the size of the machine this is running on, what happens when you run out of capacity? Which takes us to the next picture here. So this is the way Identity Cloud scales. So on top here, we have the clustering out of the box for a single processor. And again, you specify workers per core, but again, that'll eventually run out as you're growing. So beyond one processor, you can now put together individual nodes on separate physical machines. And it becomes very simple because of the statelessness and the way we do state handling. All these two identity nodes here, I've got two shown here, and you could expand this to as many as you want, to infinity, or as many as your application can afford. And all we have to do is specify that we're sharing the same Redis instance and the same Redis namespace, which are parameters you set up. And you set up each of these nodes identically so that when they start up, they're sharing the same Redis instance, and voila, you have now doubled your capacity. And again, you can keep scaling this thing as large as you want. Of course, when you do that, you need a load balancer, and these are running in a Docker, at least the recommended way is we run these in a Docker container, and then we use Kubernetes to handle the orchestration with the load balancer. But at this level, of course, the load balancer is taking transactions and routing them to the next available node, and then that node is routing to the next available worker, and the work gets done. So it's very fast and very efficient. Once you get past this scale, it kind of begs the question, okay, now how do I scale the rest of my application? Well, Redis, eventually you might run out of Redis capacity, in which case that scales individually. And that's elastic scaling. So they scale up and down, and so is IdentityJS. So as you're using these nodes, let's say you scaled up to 10 at maximums, later on you find out you only need 7, well then you would dynamically decrease the number of nodes to 7, so you're only using what you actually need. You're not paying for anything extra. Similarly with application databases, Oracle is a good example, one that does elastic scaling, so you can scale your Oracle database separately from your Redis database and separately from IdentityJS. So this is independent, basically independent scaling, and I'll show another picture of that here, I think. Yeah, here's a good example. This is elastic scaling with high availability, no single point of failure. So this is the way you would deploy in any practical configuration where you don't want to have a single point of failure. So you would have 2 identity nodes minimum, and this would be for production. So in a development or test scenario, you wouldn't necessarily need them be clustered this way. You'd get the same functional equivalent without it, of course. But if you want production to be hardcore and no single point of failure, then you're going to want a minimum of 2 of these. And same thing for your load balancers, all the way out here to the network interface. So again, identity nodes scale at 2 levels within the processor, and then you can add multiple nodes, which then link to the same Redis instance, okay? And this is separately scalable. So these little arrows here meaning it's elastic. They scale up and they scale down. And I think of it like independent suspension on your car. Your wheels are independent suspension. And so if I were to need more IdentityJS bandwidth because of my application, I don't necessarily need additional Redis database, depending on what I'm doing here. Conversely, I may not be increasing what I need here, but based on my code, I need more application bandwidth, okay, application database bandwidth. So this scales independently of this, and it scales independently of this, so they're all scaling independently, which is exactly what you want to minimize your costs. So we're cross-coupled to load balancers. Load balancers are running floating IP to dynamically swap on faults and things like that. So you're getting the most out of your load balancers. And again, Redis and the app databases are IP addressable and also independently elastic scaling. So this is, in a nutshell, a simple example of a fault-tolerant, no single point of failure architecture that we recommend. And again, you can scale well beyond this, right? So you can just keep scaling this thing, again, to the point that your application needs and can afford. Okay, so we've established that IdentityJS can provide some significant productivity increases. A number of factors involved there. We're using just JavaScript, so everything is the same source code, nothing to compile. It's a write it and run it technology. We're sharing the same code across all devices, so there's nothing different between smartphones and browsers, and nothing between browsers and native applications. It's all running the same code. And of course, there's the issue of continuous upgrades using what we call software by reference. So now it's time to consider performance of the system relative to the old way of doing things. And the most recent old way of doing things is something called serverless technology, which was advanced by Amazon in AWS and has been, I think, taken up by most of their competitors. Serverless is an interesting name. I believe it's a misnomer. It actually runs on lots of servers. What they were trying to say is that it was administratively serverless, and which is probably why they didn't call it that. So, serverless basically means they've hidden from you the need to administer servers, which on the face of it sounds like a good thing. It also has its Achilles heel. So basically all of these serverless architectures are a mapping of functions, a mapping of sets, two sets. There's on the right you have a set of M functions mapped on top of N processors, where their M is greater, and in fact it's much greater than N, right? So you could have hundreds or thousands of functions, of serverless functions defined that get allocated to a processor at runtime. And this mapping occurs in real time for every function invocation. And it's further complicated by new versions, as you can imagine. The issue of, when you decide to invoke a function, internally you have to decide what processor that function is going to run on. Or first of all, find out it may already be on a processor, and you may be able to reuse that function. But that's all complications when it comes time to actually running them and managing this thing. It also leads to the notion of cold starts, which I talk about here. So if you're not sure a function is already running on a processor, then the first time you run it, you have to start it up, and that's the cold start issue. It also means you can't cache system-level state information, and by that I mean an example would be a database connection. So in IdentityJS, you can cache your database connections so that you don't have to reestablish that connection on every transaction. Here, you're not sure. So if your function is running, is the first time it's being run on a new processor, then you have to establish your database connection. So some interesting complications involved. This mapping also means that it's difficult, if not impossible, to handle hybrid situations, since public and private have their own maps. It also leads to problems when you try to run dedicated versus shared, because of course they want to be serverless, so they're running always in a shared environment. So with that as background, let's go to the next slide here and look at the way IdentityJS performed relative to serverless. The red line here is meant to mean serverless, and it grows relative to system load in a linear fashion, right? So I'm using dollars per day, but you can use whatever metric you want, dollars per minute or dollars per month or whatever. I just chose dollars per day as an example here. So given as your load increases, you're going to be using more and more server functionality. You won't know which servers you're running on, again, because they're serverless. You don't know from an administrative standpoint what server you're running on. Conversely, the blue line here is the way IdentityJS grows with system load. So serverless cannot take advantage of dedicated resources by virtue of the fact it's serverless. IdentityJS, on the other hand, can take advantage of dedicated servers without you having to know how to administer them. So you can imagine both of these are starting out using a single shared server. And that's how you would start out. If you, as a function of system load, you would start out both systems. Now, I'll maintain that IdentityJS is always going to be less than serverless, even though there's only one shared server, because we've offloaded, as you recall, we've offloaded all the UI processing effort from the server down to the client. So you can imagine going back to the Amazon issue with 6 million people trying to run during Amazon Prime Day. Imagine you had those 6 million users running half of the load on their device, which is what IdentityJS does. Well, suddenly you'd find you're using a lot less server because you're using those free, and I put that in quotes because it's free to the person offering the service. It's obviously not free to the user, but those devices are very powerful and getting more powerful, and the functionality is there to, as we've demonstrated, to run the complete UI functionality. So I maintain this blue line will always be lower than the red line for any value on system load here going off to the right. So then you have these inflection points. So basically you're running shared up to the point where the cost of running any more shared any more shared resources is going to exceed what you'd have for a dedicated. So now with IdentityJS, we can shift you to a dedicated resource, and you're running along this line until you reach the point that you're going to need, and this is a parameter you can specify. Let's say you use 80%. So when the processor reaches 80%, you need more processing power, at which point we'll add a dedicated, or add another shared segment here, and you'll keep growing until you've used that shared processor to the point where a second dedicated processor is more economical than increasing this way. So now it's a step function, and now you'll be moving up this line. You'll now add your second dedicated server, and you're moving horizontally here until a point at which you hit 80% utilization of that dedicated server, in which case you add back the shared server. So as you can see, you're growing, never using more than one shared server, adding dedicated servers as necessary, but your software doesn't know that, and there is no administrative burden with this architecture, knowing that you're using a dedicated server versus a shared server. So at all points, even down here, IdentityJS is better than anything serverless can do because we've offloaded and we're using the client processing power to offload the servers. And of course, at this point, we get much better because we're using dedicated, and we're not following this ramp up to forever, right? We're actually making steps here to get you the best possible price performance. So I thought I'd spend one slide on software by reference, since we've mentioned it several times. By analogy, today we synchronize our data in the cloud. Everybody has email and calendar items, for example, synchronized. So if I were to add an event to my calendar, I would expect it to be available to any device, right? So if I'm on my phone, I get to see it, and if I'm sitting at my desk at my computer and I look at my calendar, it's there too. And I change it one place and it's available the other. Similar with emails. So why can't we do the same thing with our code? And that's what software by reference is all about. Basically, it's a concept of a single code server URL that supports all devices. And a code server is really just a web server. We're serving up static JavaScript files here. It's not rocket science, right? So, but we're also serving up version management capability with those files. And we could get into that later. But basically, you manage your code. You push up a new version, including a new version identifier. And as soon as you do that, if it's a UI, if it's your UI code server, then all your devices are upgraded. all of your customers' devices are upgraded. If it's a server code server for the URL for your servers, then they all get upgraded at the same time. So basically, all code, client and server, is managed centrally and cached upon reference. So what this means is you synchronize version manage for both client and server from a centralized URL. So IdentityJS objects are shared by reference, and all references are updated on the fly. So as soon as I push new code, let's say from development to production, or let's say I go from development to staging to production, we'd still recommend, in general, you have 3 levels. You have a development code server URL, you have one for staging, and you have one for development. So let's say you're pushing code, you're through with your staging, testing, and you're ready to go push those changes in production. You simply push those to your code server, your production code server URL, and instantly all devices and servers referencing that code get the upgrade. And so that's why we call it continuous deployments. So let's end with where we started. IdentityJS is a portable platform as a service. And that's important because it means we can support public, private, and hybrid configurations. It also means we can support dedicated and shared, in which you saw in terms of the economics of the system when you're operating it at the server side. It means we can get you the best possible price performance using a combination of shared and dedicated processors. And hopefully you've seen that what we can do is reduce cloud development and maintenance costs by a factor of 10. And by offloading all the UI processing to the free devices that users are carrying, we can boost server performance by a factor of 2. Appreciate any questions you might have. My email down here is dave@identityjs.com. And the website, of course, is IdentityJS.com. If you want to take a look, and there's a lot of information there, a lot more than we covered today, of course. And give me a shout if you have any questions. Thank you for watching.